Hey everybody, I'm Stephan, author of The Great World History Book. Given that I'm a trained astronomer, you might find it interesting to get my take on the greatest astronomer from the ancient world, namely Ptolemy. And in this lecture we'll look at his greatest work, which is named the Almagest. Let's dig right in. So, let's start with a depiction. This one is from the 16th century, hundreds and hundreds of years after his death. Here we see Ptolemy looking at the stars, and behind him we see the goddess Astronomia. So, who was Ptolemy? Ptolemy lived in the 1st and 2nd century AD, and he's considered to be the most important ancient astronomer. He was born in Alexandria in Egypt, which at the time was part of the Roman Empire, and he was of Greek descent. His model of the solar system was remarkably accurate at predicting the complex motions of the planets. It remained dominant for 1200 years until it was finally replaced by the heliocentric model of Nicholas Copernicus. Ptolemy's main work is called the Almagest, and it is one of the most influential scientific texts in world history. The current title, the Almagest, is actually not the original title. It is derived from the Arabic translation of the work. And that title was Almagesti, meaning the greatest. And that in the West later turned into Almagest. The Almagest is a massive work, hundreds of pages thick, filled with extensive astronomical tables and complicated figures. And today I made a massive effort to make this complex topic very clear and understandable for you today. Here we see one of those tables from a 16th century version of the book. And here we see another one. And then finally here we see a piece of text supplemented on the side with these complicated mathematical drawings that depict the motions of the planets. And we'll get into some of what these complicated drawings mean later on. But let's start at the beginning. Ptolemy starts his work with an analysis of different types of knowledge. It begins relatively simple. The first line reads, "Those who genuinely engaged in philosophy, Cyrus, seem to me quite rightly to have distinguished the theoretical part from the practical part of philosophy." Cyrus is the name of a man, we don't know who it is, but it seems he has dedicated his work to this person. He then further divided theoretical knowledge into three different types: theology, physics, and mathematics. Only mathematics, he claimed, gives us true scientific knowledge. We read, "One might call the other two kinds of theoretical knowledge conjecture, so unsure, rather than scientific knowledge. The theological, because it is utterly suprasensible, it's beyond the senses, and it is unobtainable. And the natural, meaning physics, because it is unstable and obscure in matter, meaning that things that happen on this earth, they are all transient, they perish. For this reason," he continues, "those who pursue philosophy would never hope to come to agreement about them," so about theology and about physics. "But the mathematical kind alone," he continues, "provides certain and steadfast knowledge to those who practice it, as its mode of proof arises through indisputable paths, arithmetic and geometry." And those indisputable paths are, of course, the logical, certain side that mathematics has to it. He then continues, and this is a very Greek thought, "With regard to virtuous conduct and character, this science, mathematics, above all things, could make men see clearly. From the constancy, the order, the symmetry, and the calm which are associated with the divine, it makes its followers lovers of divine beauty, accustoming them and reforming their natures, as it were, to a similar spiritual state. So the beauty of the divine helps people cleanse their souls, basically." Now let's build Ptolemy's system step by step. First of all, following Aristotle, Ptolemy recognized the Earth as a sphere. That is a very important starting point. We read, "The Earth too is sensibly spherical, for it is not possible for all observers on the Earth to see the sun, the moon, and the rest of the stars rising and setting at the same time. And he continues, rather, those living in the East invariably see them rise and set earlier, while those in the West later. This of course makes sense on a globe. If you change your position, you're going to see different stars. He continues, the farther north we travel, the greater numbers of southerly stars are hidden and the greater number of northerly stars are revealed. So if you move east-west, the setting and rising of the stars changes, and when you move north and south, different stars appear and disappear on the horizon. He continues with even more evidence of the spherical Earth. Eclipses, he continues, that occur at the same time are not recorded by all observers at the same hour. And since the difference in the hours is found to be proportional to the distance of the regions, one might reasonably suppose that the surface of the Earth is spherical. And finally, one last proof. If we sail towards mountains, their magnitudes are observed to increase gradually, just as if they were rising out of and had previously sunk into the ocean itself or the sea itself, due to the convexity of the surface of the Earth. This phenomenon is depicted in the photograph below. We see, I think, the city Toronto, and when you see it from a large distance, it is as though the bottom side of the buildings is hidden behind the curvature of the Earth. And when you move towards the city seems to rise out of the water. And this is what Ptolemy was describing, using a mountain instead of a city. And here, by the way, we see a 16th century example where they've used a ship that seems to arise from below the horizon. So we've established a spherical Earth. Now let's look at the stars. If you follow the stars at night, they seem to rotate around us every 24 hours, making a full circle, as you see in the picture. The stars all seem to move around an axis, and this axis points, by accident, to the polar star, as you can see in the image as well. And here we see an interesting photograph of that phenomenon. If you're taking a picture, but you keep the lens open for an extended period of time, you can see the trails of the stars as they move. And you see they all seem to move around that common axial point. And very close to that point is the polar star. The polar star isn't exactly in the center, but it's close to it. The stars all seem to move in unison, leaving the distances between all those stars constant, and that is why we have consistent constellations that people made up. Anaximenes in the 6th century BC had explained this phenomenon by assuming that all the stars were stuck to a crystal sphere that was rotating around every 24 hours. Today we know, of course, that the motion of the stars is just apparent. The stars seem to move, while in fact it is the Earth that is rotating around its own axis. But of course the Greeks did not know that. Secondly, there's a very slow motion of the stars known as precession, which we now know is caused by the periodic spinning of the axis of the Earth every 26,000 years or so. Hipparchus in the 2nd century BC had already discovered this effect. He had done this by comparing his own measurements of the stars with those of his predecessors. Thirdly, the fixed stars also make an annual motion along the Zodiac every 365.24 days. And you see that Zodiac, the belt of the constellations, depicted in the image on the right. As you can see, the Zodiac is inclined at an angle, and the angle is 23.5 degrees compared to the equator of the Earth. That also requires explanation. So what is the Zodiac exactly? Well, we now know that it is the plane of the solar system. So we have the sun in the middle, and the planets that rotate around it all move in one two-dimensional plane. And that is the plane that we see inclined at an angle from the Earth. So how does this cause the stars to slowly shift during the year? Well, as the Earth revolves around the sun, as you can see in the image on the right, the night side of the Earth, the side that is pointing away from the sun, points to different parts of the sky at night, making different constellations visible. So for instance, the right Earth in the image has the night side on the right side, so it looks at the constellations on the right, while the Earth on the left instead has the night side on the left side, and he looks at totally different sky. Finally, you have to answer why that zodiac plane is tilted compared to the equator. Well, that's not because the solar system itself is tilted, it is because the Earth is tilted in comparison to that plane. You can see that in the image as well, and the tilt of the Earth is exactly the same 23.5 degrees that we've discussed earlier. As I've told you before, the Sun, the Moon and the planets, they all move along this zodiac, as you can see in the image. The Sun appears to orbit along this zodiac every 24 hours, of course, and this is of course also because of the rotation of the Earth around its own axis. But the orbit of the Sun is a little bit more complicated than that. This is because that tilt of the Earth also causes the orbit of the Sun to shift back and forth during the year, as you can see in this image. It shifts furthest north in June. This is called the summer solstice, and it shifts further south in December, which is called the winter solstice. When the orbit is right in between those two solstices, right in the middle, we speak of an equinox. There's one equinox during spring and another one during autumn. During the summer solstice, as we've just seen, the orbit of the Sun reaches highest north, giving the northern hemisphere maximum sunlight, causing their summer there. And here we see that phenomenon. On the right we have the summer solstice, because the Earth is tilted a little bit towards the Sun, that northern hemisphere receives more direct sunlight. The Sun appears higher there above the horizon, and that is how the seasons are caused. Similarly, during the winter solstice, the orbit of the Sun was highest on the southern side. At that point, it gives the northern hemisphere a minimal amount of sunlight. We see that on the picture in the left. When the Earth is tilted away from the Sun, now the southern side experiences summer and the northern side gets lesser sunlight. The Sun appears lower on the horizon, and that is why we have winter there. And then finally, let's look at those equinoxes. We have a spring equinox, as you can see in the image, and an autumn equinox. And in both cases, the Sun shines straight on the equator, as you can see in the image. And this is causing day and night to be of equal length. This is the only time where you have a 12-hour day and a 12-hour night everywhere on the planet. In fact, the word equinox means equal day. That is an easy way to remember it. So we have a spherical Earth, we have stars rotating around it in complicated manners, and we have a Sun that orbits around it. Now Ptolemy wondered, that Earth, is it centered at the center of that sphere of the fixed stars? He believed this was the case because we always see exactly half of the zodiac. If this is the sphere of the stars and we're centered right in the middle, when you're standing on this side of the Earth, you see the half of the zodiac, and when you stand on the other side, you see the other half. If instead the Earth was more to the side, you would see only a small part of the zodiac during one half of the day and a larger part of the zodiac during the rest. Also, if the Earth was right at the center, day and night would not be of equal length during those equinoxes. If the Earth was centered, for instance, right here, then the Sun would have just a very short orbit on this side and a very long orbit on the other side. So this was his proof that the Earth was in the center of that sphere of the fixed stars. Very interesting idea. But now Ptolemy went astray. Since the Earth is always at the center of that sphere of the fixed stars, it must be at rest, he reasoned. We quote, "Assume that for argument's sake the heavens are unmoved, while the Earth revolves around the same axis from west to east. Such a thing would seem quite ridiculous based on what occurs around us and in the air." So he actually had the correct idea that it was revolving around its axis, but then he called it ridiculous, and for the following understandable reason. The revolution of the Earth is the most violent of all motions, he says, causing everything not standing on Earth to make a single motion opposite to the Earth. So, if I would throw up a ball while the Earth is rotating, shouldn't that ball just fly all the way to one side? A very reasonable idea, and one that was only solved by Galileo hundreds and hundreds of years later. To refine his model even further, Ptolemy also had to include the observation that the Sun and the planets speed up and slow down along their paths. This he called animalistic motion. Hipparchus in the 2nd century BC had already measured this by measuring that the seasons were of slightly different length. It took, for instance, 94.5 days from the spring equinox to the summer solstice, while it only took 92.5 from the summer solstice to the autumn equinox. And these changes in the time of the seasons were caused by a speeding up and a slowing down of the Sun. From this observation, Hipparchus concluded that the Earth was not in the center of the solar orbit. So if you have the orbit of the Sun around the Earth, like this, the Earth was not in the center, but slightly off-center. He calculated that it must be off-center about 1/24th of that solar radius, of the radius of the orbit of the Sun. In addition, the planets also exhibit what is called retrograde motion. If you, for instance, follow the planet Mars, you'll see that it will continue along its orbit for a period of time, but then it will slow down and stop, turn backwards for a moment, and then finally continue in its orbit again. This backward motion is called the retrograde motion, and it is observed in all the planets. This makes the motion of the planets insanely complicated. Here we see an 18th century drawing of some of the planets, and you see how complicated those orbits tends to be. This is the Earth in the center and some of the planets circling around them. In the 3rd century BC, Apollonius, another astronomer, had described this retrograde motion with what is called epicycles. An epicycle is a small orbit, as you can see in the image, that is rotating along a larger orbit, creating those circles. So this was a mathematical mechanism to better understand what was going on. It was as though the planets moved on a circle within a circle. In the 4th century BC, Plato had challenged the intellectuals of his day to attempt to explain these animalistic motions of strange retrograde motions and so on in terms of simple circular motion. He was convinced that there must be a way to simplify that messy movement of the planets, and Ptolemy finally took on this challenge. We quote, "It is necessary to premise in general that the motion of the planets eastward in the heavens are all uniform, meaning of constant velocity, and circular by nature." So this was Plato's challenge. And then he continues, "They are uniform either on circles non-concentric with the universe." This was Hipparchus' idea that the orbit of the Sun was slightly off-center. Or else on circles that are concentric, but not upon them simply, but rather upon circles carried by them and called epicycles, so circles in circles. So he actually names those two ideas from Hipparchus and Apollonius. So firstly, Ptolemy follows Hipparchus in placing the Earth off-center, as we see on the image in the right. The plus sign is the center of the orbit of the Sun, and the Earth we've drawn just below it. Ptolemy then added the equant, which is his most important contribution to this system. From this point, we see the equant slightly above the center of the orbit of the Sun. The motion of the Sun appears constant. So whether the Sun moves from A to B or B to C, it seems to move at the same angle, as you can see in this image. While as seen from the Earth, the same motion suddenly appears non-uniform. So if we look at the same motion in this image as seen from the Earth, we now see that the motion from A to B appears smaller, at a smaller angle than the motion from C to D. Ptolemy then showed that this model approximated the observed motion of the Sun extraordinarily well. And Plato must have been very happy with this model, for as seen from the equant and from the equate only, it seems as though the Sun was moving at a constant velocity. And now things get really interesting. Some details which Ptolemy mentions clearly in his text already hint at the heliocentric model of the solar system, but he just couldn't see it, even though it was right there in his own writing. For instance, Ptolemy tells us that Mercury and Venus, the inner planets, always stay very close to the Sun. Mercury always stays within 28 degrees of the Sun, as seen from the Earth, and Venus within 47 degrees. So they always stay close to the Sun. Why is this? This is because they're orbiting the Sun. Why else would they always stay close to the Sun? But even though Ptolemy knew this fact, he did not make that conclusion. Similarly, Ptolemy notes that the mean motion of the inner planets, the motion of the planets around the Earth, is equal to the mean motion of the Sun. This is of course for the same reason that the planets are orbiting the Sun, so obviously the rotation time of the Sun is the same as the rotation time of that planet as seen from the Earth. In fact, and then it becomes even more clear, the center of the epicycle of Mars and Venus, the inner planets, is the Sun itself. It is revolving around the Sun. But unfortunately, Ptolemy did not know this. He actually believed that the inner planets were rotating below the Sun, like this. So this is the Sun and this is the... He didn't know the distances to the planets, so you cannot blame him for not knowing that the planets were actually revolving around the Sun, for then the heliocentric model would be immediately clear. But yeah, he didn't know that. Thirdly, Ptolemy also knew that the radius of the epicycle, you can see an epicycle on the top right in the image and you see its radius, is always parallel to the radius of the Sun. So in the middle, or just below the middle of the image, we see the Earth, and circling around it we see the Sun, and we see again that radius. And as you can see at the image, those two radiuses are perfectly parallel. Also, the epicycles of the outer planets all have periods of exactly 1 year, the same time it takes the Sun to revolve around the Earth. This is again clear evidence of the heliocentric model. For the planet simply seems to move with the Sun, and from this we can easily imagine that seeing this motion from the Sun, from the perspective of the Sun, that strange epicycle movement would immediately disappear. In this drawing, I've also shown that the orbit of the Sun is actually exactly equal to the orbit of the epicycle of the outer planets, but Ptolemy also didn't know that. So Ptolemy knew about all these curious coincidences. The inner planets, the outer planets, they all have something to do with the orbital time of the Sun itself. So he mentions all this, but he saw no need to explain it. He simply posits those facts as just attributes of the planets. But he was so close in seeing the bigger picture. Finally, I want to quickly discuss another work by Ptolemy known as the Planetary Hypothesis. Ptolemy attempted to measure the size of the universe in this text. To do this, he used the assumption that the spheres of the planets were all stacked on top of each other. In this way, there was no vacuum between those spheres, which Aristotle, earlier philosopher, had claimed did not exist in nature. So he believed that those spheres of the planets must be stuck on top of each other to avoid a vacuum. Using that assumption and estimating the sizes of those epicycles, he could then calculate the distances to the planets. We quote, "The distances of the planets may be determined without difficulty from nesting the spheres, adding the spheres on top of each other." He then equated the distance to the sphere of the fixed stars with the radius of the cosmos. So he thought he was calculating the radius of the cosmos itself. His results, of course, these distances were way off. But it was an ambitious attempt nonetheless, and that's why I wanted to mention it in the end. So this was it for today. If you want to know more about world history, then get a copy of my book, The Great World History Book. See you next time. So in order to better understand that strange retrograde motion of the planet, that complex motion that you see right here, I created a JavaScript model. I did this the easy way. I first created a Copernican model with the sun in the center and then all the planets revolving around this. I used the real values of the planets, so the real velocity, the real distances, and so on. And then I made what is called a coordinate transformation, where I use simple mathematics to view what this motion looks like as seen from the Earth. And that's just a few lines of mathematics, and then you immediately get from this to this insanely complicated picture. Well, let's first look at the inner planets so you better understand what's going on in those lectures. So let's look at Mercury first. Let's slow it down here. As mentioned before, we can easily see that Mercury is rotating around the Sun. Well, Ptolemy didn't know that. He thought that Mercury was rotating somewhere here, but this is very clear evidence of the heliocentric model right there. It is revolving not around the Earth, but is revolving around the Sun. The same goes for Venus. So here we see Mercury and Venus, the two inner planets, both circling around the Sun. It takes a slightly bigger orbit. You can see it creates beautiful patterns, and the pattern of Venus is especially beautiful as it creates a four-pointed flower that we'll see in a moment. So here we have the fourth side, and then we get the last one right here. So here we see that five-pointed flower. It's pretty incredible. A good idea for a tattoo, in fact. So let's now look at the outer planets. Here we have Jupiter and Saturn. We also have Mars, but Mars is a bit more complicated to understand. But in the end, it works in the same way. So what do we see here? We see that the motion, the retrograde motion of Jupiter and Saturn perfectly mimics the motion of the Sun. And that is because, of course, we actually have to view this motion as seen from the Sun. This is the actual motion of those two planets right here. And the fact that they move so similarly with the same rotational period in the same direction is also evidence for that heliocentric model. See you next time.